stargazers and space experts are stunned by the looming vanishing of the North Star, Polaris. This occasion is expected to be the next huge thing in the world of astronomy. Yes, you heard that right, Polaris is going to be focused on our starscape for good, and this approaching celestial calamity carries significant implications for our ground-based telescopes, which use it as a source of perspective for their adjustment and accuracy. Brian Cox warns that the Polaris explosion is imminent and will change the night sky forever. Let's dive deeper into the tale of the North Star and why its end matters so much. For centuries, Polaris has been a guiding light for both astronomers and navigators. However, all of this might change in a matter of decades, if not years. A new research paper presented to the esteemed Royal Astronomical Society in September 2023 has essentially sealed the fate of this guiding light. Polaris is on the brink of a disastrous event, a blast that could result in its vanishing from the night sky forever, modifying our cosmic compass. Before we explore the potential outcomes of this revelation, let's examine the star in question, also known as the North Star or Pole Star. Polaris holds a unique position in our night sky due to its proximity to the celestial North Pole. It sits directly above the Earth's North Pole, giving the illusion of being almost fixed in the northern sky. Situated in the Ursa Minor constellation, which is also known as the Little Dipper or the Little Bear, Polaris shines as a moderately bright yellow-white supergiant star. It outshines the Sun in luminosity, emitting significantly more light across the astronomical spectrum. In terms of sheer size, it dwarfs our Sun, boasting a radius estimated to be multiple times larger. Despite its apparent peculiarity, Polaris is part of a complex triple star system. Two of these, Polaris A and Polaris AB, appear as a single star to the unaided eye, while a third companion, Polaris B, orbits this double pair. The intricate gravitational interactions among these stars impact their orbits and luminosity. However, the specific elements behind these interactions remain a cosmic mystery. On top of all this, the astonishing distance of Polaris from our planet adds a fascinating temporal twist to our understanding. Since it is 323 light-years away, the light we see from Polaris today left on its interstellar journey over 3 centuries ago. If we were to see Polaris explode right now, it would have actually done so all those years back. Earth, back then, was very different. In the mid-18th century, humanity was navigating through a period marked by significant historical events and social movements. It was a time characterized by the end of the Renaissance, the start of the Enlightenment, and the beginning of the Industrial Revolution. In some parts of the world, scientific advancements were gaining momentum, with figures like Isaac Newton forever changing the scientific landscape. Daily life and society were still largely agrarian, with farming being the primary occupation. However, urbanization was increasingly taking hold, leading to the growth of cities and the expansion of trade. Socially, music and art were finding prominence. So, if Polaris were to explode tomorrow, it would have indeed concluded its life while Earth was in the midst of a time of change and exploration, paving the way for the advancements that would shape the centuries to come, similar to how this event would change things for our future. Throughout the centuries, the North Star has woven its importance through the tapestry of civilizations across ages. This stellar guide has served as a guiding light for ancient sailors and explorers, illuminating their paths across vast seas and uncharted territories. Polaris has been a reliable beacon, guiding navigators in the Northern Hemisphere and enabling them to chart courses with confidence. It has exemplified a cultural and navigational foundation for millennia and has shaped the stories of ancient adventurers, storytellers, and scholars alike. So, how do we know that the star is approaching its end? Named a Cepheid variable star, Polaris has quite specific properties and measurements. Its anticipated brightness changes have been instrumental in unraveling mysteries about variable stars and calibrating astronomical instruments. These rhythmic pulsations have traditionally followed a dependable pattern, aiding cosmologists in predicting its behavior with ease. However, in the aforementioned research paper, scientists revealed a deviation from this normal pulsation cycle that has startled the astronomical community. Polaris has taken on an erratic, capricious rhythm of darkening and brightening. This abnormality has prompted intense investigation, with astronomers scrambling to understand this celestial irregularity. This departure from its norm has raised concerns among researchers, suggesting that Polaris may indeed be moving toward the sunset of its existence. Its pulsation period has recently begun to extend. The star was previously stable in its cyclic brightness shifts, but now astronomers have noted a gradual elongation of the pulsation length, with an annual increase of 4.5 seconds. While seemingly minute, this change holds significant cosmic implications, indicating a major departure from its established behavior. There have been several hypotheses regarding this matter, including a natural shift due to gravitational interactions within the Polaris star system. These interactions could be adjusting the star's atmospheric conditions, directly impacting its pulsation patterns, or, more alarmingly, indicating a looming celestial explosion. The abnormalities in Polaris's behavior have ushered in a new era of cosmology, set to change everything we thought we knew about triple-star systems like Polaris. Discussing how discoveries change our perspective, in 2006, astronomers had a close look at Polaris courtesy of the Hubble Space Telescope. They also uncovered the elusive companion star settled so closely to Polaris that it had been difficult to detect previously. This was the very first image of our celestial neighbor, capturing its brilliant light. We now know that the companion Polaris B orbits the central trio at a distance of around 2 billion miles. Although cosmologists had inferred its presence from light studies of the triple star system nearly a decade ago, its faintness compared to Polaris had hindered direct observation until the Hubble Space Telescope made it possible. This all began with the launch of the Hubble Space Telescope, HST, in 1990. Its deployment opened a window to the universe, providing unmatched clarity in redefining our understanding of astronomy. The HST captured wonders that reshaped our basic comprehension of space, include notable accomplishments like the awe-inspiring image known as the Pillars of Creation in the Eagle Nebula, which houses enormous clouds of gas and dust where stars are born. Another milestone moment accompanied the discovery of the Hubble Deep Field, an apparently empty patch of sky that, upon closer investigation, was overflowing with thousands of galaxies. This single image expanded our understanding of the universe's sheer immensity and complexity. The Hubble Space Telescope, HST, also studied exoplanet atmospheres, revealing tantalizing clues about their composition. The presence of elements like water and organic molecules in these distant realms indicated the enticing potential for habitability beyond our solar system. Building on the legacy of Hubble, its successor, the James Webb Space Telescope, JWST, was launched to push the boundaries of technological advancement further. With lessons learned from Hubble's endeavors, the JWST is poised to delve deeper into the mysteries of the universe, continuing the tradition of exploration and discovery started by its esteemed predecessor. One of the JWST's champion features is its unrivaled ability to capture cosmic vistas with striking clarity, banishing the dark shadows that once obscured our celestial perceptions. The telescope operates primarily in the infrared spectrum, piercing through cosmic dust and revealing celestial treasures previously hidden from human sight. At its core lies a giant 6.5-meter primary mirror made of 18 hexagonal segments, surpassing Hubble's mirror in sheer size and sophistication. Positioned about 1.5 million kilometers away from Earth at the second Lagrange point, L2, the JWST effortlessly trails Earth's orbit around the Sun. From that vantage point, it provides us with an unobstructed and vigilant eye into the cosmic web. However, the journey into the universe isn't just an excursion across light years, it's an excursion through time itself. The JWST utilizes cutting-edge infrared instruments capable of looking back billions of years into the past, capturing the ancient light produced by celestial bodies as the universe expands. This light undergoes a transformation known as redshift, moving from its original visible spectrum to the infrared frequency or longer. The JWST is perfectly suited to detect and interpret these infrared signals from distant celestial objects. It is now set to transform our understanding of the cosmos as it reveals clearer than ever images of distant stars and galaxies. This innovative telescope has heralded a new era of galactic exploration, ready not only to uncover the far reaches of the universe but also to unravel the secrets of our vast past. With its extraordinary capabilities and unique vantage point in space, The James Webb Space Telescope stands as a testament to human ingenuity, opening the secrets concealed within the cosmic expanse. So far, we know that there are intriguing parallels between Betelgeuse and Polaris. Both of these giants are expected to approach their ends. Betelgeuse, a prominent star in the Orion constellation, has exhibited puzzling anomalies in its brightness, similar to what we've observed in Polaris. This similarity has prompted scientists to consider the possibility of an impending explosion, raising concerns about Betelgeuse's inevitable fate. The uncanny likenesses between the brightness variations and patterns displayed by the two stars certainly attract attention from astronomers worldwide. Toward the end of their lives, stars often exhibit such irregular behavior despite their historical consistency. These celestial entities undergo significant changes in luminosity as they approach the end of their cosmic journeys. NASA has closely studied Betelgeuse's anomalies and raised the alarm. However, the agency's heightened concern regarding the potential explosion of Betelgeuse stands in stark contrast to their indifference toward Polaris. While NASA has dedicated significant attention and caution to Betelgeuse's strange behavior, a comparable level of investigation and official concern has yet to be announced regarding Polaris. Regardless, the intriguing parallels between these two celestial phenomena offer a captivating glimpse into the secrets of stellar evolution. As astrophysicists explore these cosmic irregularities, the striking similarities between the evolutionary paths of Betelgeuse and Polaris raise difficult questions about the nature of these stars and the certainty of their celestial destinies. Stars undergo distinct stages in their developmental journeys, starting as infant stars with subdued temperatures and brightness. They progress into the main sequence stage, where they burn hydrogen fuel through nuclear fusion for billions of years. However, as their hydrogen reserves diminish, they enter the red giant stage, characterized by a dramatic increase in temperature and brightness. This red giant phase is the prelude to a spectacular grand finale, usually a cataclysmic explosion known as a supernova. Some stars shed their outer layers in a stunning display before the massive explosion, leaving behind a dense core known as a white dwarf. Regarding Polaris, researchers have suggested that the star has begun the phases of helium exhaustion, a phenomenon seen in most Cepheid stars nearing the end of their lives. As a Cepheid star runs out of its stable helium supply, it experiences irregular pulsations, appearing as fluctuations in its brightness. This exhaustion triggers a series of events, resulting in unpredictable light emissions observed in Polaris. While these anomalies align with behaviors typical of Cepheid stars approaching their twilight stages, substantial evidence of Polaris entering the definitive phase of its life cycle is still to be uncovered. Cosmologists are investigating and unraveling these anomalies to clarify the impending fate of Polaris and gain further insights into the mysterious behaviors of such stars. If Polaris were to undergo a supernova event, it would be a magnificent spectacle for all to witness. Suddenly blasting with tremendous force, it could indeed surpass the moon's brightness, emerging as one of the most brilliant objects in the night sky for days, weeks, or even months. The transformation of Polaris during this cosmic spectacle would also be exceptionally dramatic, displaying vibrant colors before gradually fading away. This celestial event could temporarily disrupt the familiar patterns of the Big Dipper or Ursa Minor, given Polaris's current role as the North Star and its association with these notable constellations. In terms of our safety here on Earth, there's no need for concern, considering Polaris's distance and mass. Earth would likely remain safe even in the event of an explosion. While a Polaris supernova may not impress as dramatically as one involving Betelgeuse, it could nonetheless persist as a display to the naked eye for a considerable period. The scientific community, cosmologists and observatories worldwide, would undoubtedly be captivated by this phenomenon. While there may not be any direct effect on Earth's environment or immediate surroundings, the death of Polaris would surely leave a lasting mark on the night sky. So, what will happen to Polaris itself? In contrast to the ordinary predictions, cosmic explosions shut down sections for enormous stars. Polaris is probably not going to meet this hazardous destiny. Normally, when enormous stars go through a cosmic explosion, it results in an enormous blast. This upheaval scatters heavy components, bringing about the introduction of neutron stars or black holes. This occurs after the core collapses in high-mass stars, multiple times the mass of our Sun. When such stars run out of their atomic fuel, they break down under their own gravitational power, setting off an extreme and savage blast. Cosmic explosions are comprehensively classified into Type 1 and Type 2. The latter happens in enormous stars with thick layers, where the core breakdown causes the dangerous removal of external layers, radiating an eruption of energy and light noticeable across tremendous distances. However, a Type 1 cosmic explosion occurs in binary star systems and a white dwarf, leading to an unexpected combination response when the white dwarf gathers sufficient mass to go through the cosmic explosion blast. Cosmic explosions act as standard candles for estimating grandiose distances, assisting us with assessing the universe's age and extension rate. Post-cosmic explosion, a star's core collapse can give birth to either a neutron star or a black hole. A neutron star is the dense, compact remainder left behind when a massive star depletes its atomic fuel and goes through a cosmic explosion blast. Neutron stars are incredibly small in size compared to their original stars, packing a mass several times that of our Sun into a sphere with a diameter of around 12 kilometers, about 20 kilometers. The intense gravitational power on a neutron star is so strong that it presses protons and electrons together, forming neutrons. This leads to extreme density, to such an extent that a teaspoon of neutron star material on Earth would weigh billions of tons. A black hole, in contrast, is a region in space where gravity is so intense that nothing, not even light, can escape its gravitational pull. The core of the dead star collapses to a point of infinite density known as a singularity, surrounded by an invisible boundary called the event horizon. The event horizon is the final turning point. When something crosses it, it can't escape the black hole's gravitational grasp. Despite their secretive nature, black holes can indirectly reveal their presence by affecting nearby matter. For example, when a black hole is part of a double system, it can pull matter from its companion star, creating an accretion disk made up of gas, dust, and other debris that emits X-rays before vanishing past the event horizon of the black hole. But here's the scenario: Polaris has a mass roughly 5 times greater than our Sun and subsequently misses the threshold necessary for a cosmic explosion. Rather, when it finally depletes its atomic fuel, it will shed its external layers and evolve into a white dwarf. This will be a quiet transition, less a cosmic explosion's unstable showcase. A white dwarf is the remnant of a low or medium mass star that has stopped atomic fusion, compacting a mass equivalent to the Sun into the size of our Earth. Upon this transformation, Polaris will permanently disappear from the night sky. Drawing matches between the expected impacts of Polaris and documented cosmic explosion events in the past can assist us with planning our assumptions. Irrefutable cosmic explosions like SN 1054, Crab Nebula, or SN 1987A can help us analyze resulting phenomena such as cloud development and the release of vast beams following such events. We can also assess possible similarities in iridescence changes, basic launches, and their effect on surrounding grandiose conditions. This way, we can lay the foundation for understanding Polaris as a potential outcome. There is no lack of data for comparison. Analyzing light curves, spectra, and remnants from these events can assist us in projecting potential qualities for Polaris as it ends, helping us anticipate the ensuing transformative phases of its stellar leftovers. To make a robust correlation, researchers carefully examine the differences in the mass, composition, and speed of materials ejected during a star's explosion and balance it with other legitimate events. When the time comes, we'll be able to do the same for Polaris. Additionally, by researching whether Polaris's ejection would lead to nebulae or specific natural patterns, we will undoubtedly improve our understanding of its unique characteristics. Digging deeper into the life cycles of stars leading up to their end also includes studying the mass, metal content, and evolutionary phases of stars in the pre-cosmic explosion stages. By looking at these aspects of known cosmic explosion cases with Polaris, we can gain insights into potential differences or similarities in how they detonate. Another critical aspect involves evaluating the pulsation patterns exhibited by stars approaching the end of their lives. In this area, we have made extensive advancements in interpreting the fate of Polaris. This examination helps us measure similarities or deviations in unpredictable pulsations, enhancing our understanding of the potential mechanisms behind the burst. However, this natural region assessment reaffirms the similarities or deviations of Polaris's behavior in its hazardous peak. This exhaustive comparative investigation will reveal insights into the differences and explore potential results. In doing so, it holds the promise of providing important insights into the distinctive or shared aspects of this celestial event within the broader cosmic context. Embarking on the complex journey through Polaris as a massive star is a considerable challenge for astronomers. Despite meticulous observations and thorough investigation, the inconsistencies exhibited by this notable star persist as an unsolved question, defining regular explanations and projecting a puzzling atmosphere in the divine tapestry. Anticipating the exact finale of a star's life is an overwhelming task. The bewildering nature of Polaris prompts a call for deeper investigation. Cosmologists distinctly recognize the critical need to unravel the hidden components governing this remarkable behavior. Unraveling the unique conditions driving Polaris's inconsistencies is key to advancing our understanding of stellar evolution and behavior today. Polaris serves as a vital foundation for adaptive navigation and celestial orientation, and it holds an essential role. The impending uncertainty surrounding Polaris's future and the potential for a devastating explosion raise significant concerns within the galactic community. Discoveries from the Royal Astronomical Society spotlight a new frontier, demanding thorough investigation and intensified research. The confusing behavior exhibited by Polaris highlights the urgency for deeper examinations and focused research efforts. Cosmologists wrestle with the complexities of unpredictable pulsations, recognizing the importance of interpreting the unique circumstances triggering this unusual behavior and providing a definitive answer. Yet, a final answer remains elusive for the time being. Nevertheless, it is only a matter of time. The objective of our mission is to enhance our understanding of the mechanisms shaping Polaris's anomalies. If Polaris were to undergo a catastrophic event, the loss of this celestial beacon could significantly impact the accuracy of ground-based telescopes and celestial measurements. Recalibration of instruments and possible adjustments in cosmic estimates would be an inevitable outcome. The irregular behavior exhibited by Polaris has unveiled a domain of uncertainties in the cosmic realm. The approaching probability of its looming explosive end calls for heightened vigilance, coordinated research efforts, and a steadfast commitment to unraveling the novel celestial complexities that shape its whimsical behavior.